My name is Sidharth Moudgil. I'm rendering lead. I'm also the SIG-Graphics Chair as well as the TUC Chair. And also, my professional background is I've spent a lot of time on a lot of rendering engines over the years. I worked on many games. And recently, I've spent a lot of time on O3DE render. Specifically in the RHI layer, I've written a whole bunch of uh, code and technology pieces within RHI. And more recently, I've also switched to pieces within RPI as well. So for this specific presentation, I will be trying to provide an overview of the whole renderer. It is a culmination of an effort by many engineers across many years. So it's going to be sort of hard to capture it all in a 1 hour meeting presentation. So I'll try my best. I will try to go deep in some areas, but it's impossible to go sort of vertical in every specific area within the render. Okay, before I start, there have been many presentations done on Atom. I've provided a quick recap. There's one that shows how to use DCC tools and create custom materials. There's a deep dive into the path system in the RHI, which I did with a colleague of mine. There's another great one that was given very recently on the Vulkan RHI. There's another one on RPI, and then there's another one on terrain and vegetation. Some of these are old, so just be aware that the state of the render was very different when some of these presentations were done. So just be aware that the information might be stale. Okay, so before we get into the actual renderer, I wanted to lay out how the render code is set up. The initial principle when we were developing the renderer was that it needed to be extremely modular and it needed to be extremely extensible. So the idea was that anybody or any external party should be able to understand pieces of the render, be able to fix and update it, and as well as replace parts of it if needed. So what we did was we split up the whole render into multiple gems. A gem is a plugin. So it basically bundles up some amount of code and some amount of data in this one cohesive unit, and then they get pulled in as needed. And the gems essentially allow decoupling between different areas of the render. So if you only care about the material canvas, you would only look at the material canvas gem, you would fix issues within it and then update within it. If you only care about the global illumination technology, you would only care about the diffuse appropriate gem. And if you don't like the current implementation, you can provide an alternate implementation, which can just be another gem. You can even turn it into a service. You can make profit out of it, or you can just contribute because it's an open source engine. And the way it works is your core engine pulls in a gem called Atom LY integration. All the components live in the Atom LY integration. So that's why that's the LY integration, the gem contains all the components, but then that pulls in the Atom bridge, and Atom bridge pulls in all the core gems. Now, all of these circles doesn't necessarily represent one gem. One circle can represent multiple gems under the hood. The idea is that the Atom bridge is all you need, and that will pull in all the core gems. Now you can see that some of these circles are not getting pulled in because not every rendering gem in the world gets pulled in by the core default level. If your project needs vegetation, then they can pull in the vegetation. If your project needs particles, then it can pull in the popcorn effects manually when you configure your project. And the idea here is that you can actually even replace the whole render. So you would just remove the Atom bridge and pull in another render number 2 bridge, and then all the gems related to it. Okay, next. So now that you have your gem setup, you have your runtime app, and it's running O3DE. O3DE, if it's a gaming app, you'll essentially do a whole bunch of gameplay logic, networking, physics, what have you, earlier in the frame, and then all that data gets sent to the render. The render in this case is split into 2 layers, RPI and RHI. The goal of RPI and RHI is that by the end of the frame, to create a list of GPU commands. All of this work is done on the CPU side. So the end of the frame, you create a bunch of GPU commands. These GPU commands are then sent to the driver. The driver will queue it for the GPU to run. GPU usually runs a frame 1 to 3 frames behind the CPU. So let's hope it's right behind the CPU. Then the next frame, GPU will take this list, execute it on the hardware, and then the idea is at the end of the at the final command, you have your final image, which is your final output of your rendered scene. It goes on the swap chain texture, which is then displayed on the monitor. GPU can run, the reason why it can run about 1 to 3 frames behind the CPU is because you want to be able to triple buffer your renderer. So if your GPU spikes, like let's say there's a performance spike, then it doesn't block the CPU. CPU can sort of keep running. It can go from, it will do frame n+1, n+2, and then it will wait for the GPU to catch up. So it just helps better gameplay experience. So here's the hierarchy. You have your RPA and your RHI. You have all your components. These are the things that you pull in the editor. So when you have your editor, you create an entity, you essentially add a component, and that's where all the code is for the component. The component exposes all the properties associated with that specific feature. So a mesh component will expose all the mesh-related properties. And then you have a feature, all the feature processor and the RPI tech stack lives in the RPI layer. And the RPI, what the RPI layer is doing is that it's essentially allowing the feature processor to create this workload on the CPU side. And we'll go into the details further along in the presentation. And it sends this information to the RHI. The RPI and RHI are decoupled. What that means is that a developer can work in the RPI layer without having to know anything about the RHI. And then the same thing. So if you're like if you want to develop a water feature, you don't really need to know anything about the DX12, Vulkan, or Metal. You can create your passes, and it's essentially abstracted out as just some GPU workload. And then this information gets sent to the RHI. RHI takes this information. All it knows is just some abstracted out GPU workload, sends it to the DX12 gem, and the DX12 will then convert it into DX12 GPU commands. So that's sort of how the hierarchy is set up and how the information flows up to down. Yeah, and just a caveat that this specific presentation I'm doing, I wrote it thinking technical, as a technical director, if you want to evaluate this presentation, how would you do? So I'm trying to, it's great for graphics engineers, but I'll try to keep it not too vertical. So hopefully this gives you an overview of the whole render. So the RPI was built to support multiple concepts. So there's a concept called scenes. There's a concept called render pipelines. So the render pipelines is essentially, I'll go into a little bit more in detail later on, but essentially it explains all the work, all the passes that needs to run in a frame to give you the final output. And it can be different. So you can have a forward plus pipeline, you can have a deferred pipeline, you can have like Unreal uses like a material-based visibility pipeline. So you can have different pipelines, and RPS supports that. And they're all data driven. So that's the key component here. So you are easily able to, just using JSON, create a replicate. You can duplicate a current pipeline and make modification to it for your own purposes. So if you have a very specific game with specific needs, you can create a custom pipeline. RPS supports multiple scenes. So you can have multiple scenes. So in this case, you have a scene with a shader ball, and then on the left, you have a scene with the thumbnail image. So you can essentially, your render can create multiple scenes. A scene can have multiple render pipelines. And because it's data-driven, you can develop graphics features. And the idea is that the graphics features are decoupled from the pipeline. So you just have to build it once. And in theory, they should be able to work across all the pipelines. But there may be some fixes that may be needed depending on what the feature is doing. Everything is platform independent. So all of these layers, the render supports this concept of palification. So you can extend every class object and provide platform specific functionality. And RPA provides a whole bunch of debugging and profiling tools. So the idea is that you should be able to profile and debug what is going on in a given frame to help you address errors. So what is a render pipeline? So render pipeline essentially comes in this asset file. It's called, we have called main render.s pipeline.az asset. Mobile render pipeline.az is essentially your file that contains the reference to your whole pipeline. And you can follow that and you can build your own. So the custom render pipeline represents if you wanted to build a custom one. You can copy paste the existing ones, you can build a new one. The core engine comes with forward plus pipeline, but you can build a default pipeline. Actually, the Atom sample viewer had a prototype version of the default pipeline. Uh, so what do they do? These pipelines essentially reference a pass file. A pass file within it contains all the information about the layout of all the passes, how they are chained together, how they are connected, all the inputs and the outputs related to it. And then the main pipeline.pass can then point to some version of passes because you have a whole bunch of passes. Just to rely a pass is sort of one unit of GPU work. So you can think of it as a blur pass, downsample. That's essentially your that's essentially the work that your GPU does using in a multi-threaded manner. It uses multiple SIMD cores. It is a shader, which is the kernel, and it has inputs and outputs. So it will do that amount of work. And if you chain a bunch of passes, you essentially get a render pipeline. So each one of these passes can pull in whatever pass they need as needed. So this just defines the layout. So then what we do is we load these asset files and we create a runtime object out of it. So really quick overview of the RPI. You have the RPI system and RHI system. The RPI system and the RHI system are actual classes in the renderer. They are sort of the very, very top tier classes. There's an interface associated with them. So the interface is how other gems will be able to interact with RPI and RHI. Obviously, the functionality that we expose is very carefully thought out. So the RPI system provides all the technology around the pass system, the shader system, the field system, images, buffers. It has the concept of multiple scenes. The scenes hold multiple feature processors, multiple pipelines, and each pipeline can hold multiple views and multiple processes. So that's sort of the very, very simplified version of what RPI does. So it does a lot. Okay, render pipelines. So just to make sure people are aware, the current core engine, as of this presentation, supports 4 pipelines. There's a main render pipeline, which enables every feature under the sun. It is meant to be used by the high-end Steam platforms, so PC, Linux, Mac. There is the low-end render pipeline, which is a subset of the main render pipeline. It is meant to be for the lower-end hardware. So it will remove some, so like global illumination is probably not enabled by default. It has taken some liberties on disabling some features for the sake of GPU performance. There's the mobile render pipeline. The mobile render pipeline was recently immersed into development. It was built specifically for tile hardware. Your PC, Linux, and Macs, they all use something called forward GPUs. And the mobile hardwares use tile GPUs. Tile GPUs, the way they do rendering is very, very different. They use TBDR, which is tile-based rendering architecture. And that means that the same pipeline can have significant impact, completely separate performance footprint on a tile hardware. So we have to build a separate pipeline for mobile hardware. And also we made sure that it is scalable. So whatever feature we enable for the mobile render pipeline, we made sure that it was able to scale based on your device configurations. And we have a VR pipeline. So the VR pipeline supports stereoscopic views. So we have taken even more liberties with the VR pipeline, only pulled in the bare minimum. GPU is at a high, it's extremely valuable GPU cycles. So because you need high resolutions for your left eye and your right eye due to stereoscopic views. So you have to be very careful with what you enable. So yeah, so these four pipelines come with the core engine, but people, I know that folks externally have actually added more pipelines for their use cases. So an example would be an indirect pipeline. An indirect pipeline is something that a lot of the AAA games are moving towards, where all of the work that RPI and RHI are doing on the CPU, we can actually do that work on the GPU. Essentially, build your draw calls and your draw packets on the GPU and then execute them right away. So there is very little CPU to GPU communication happening. So here's my, a lot of these slides are inspired by, some of them were inspired by previous presentations and some with internal documentation. So I just didn't have time to write them all up from scratch, given the time restrictions. So here is a quick overview of RPI. You have all your components sitting at the top. Then you have your scenes. Your scene owns all the feature processors. It also owns multiple. So I only have one arrow, but you can have multiple pipelines. Your pipeline essentially owns multiple views and all the passes related to it. So pipeline objects are created from the pipeline asset file. Your feature processor is essentially working with the component to build all the draw packets. That's sort of the final job of the feature processor. These draw packets get converted to draw list. They get filtered out, culled out. Then the pipeline builds all these passes from the pipeline asset files. And then these passes, so if you have a forward pass, you're gonna need at least two views, one for the shadow, because you need a shadow view to do shadows, and then one is your primary view. And now depending on the game, you can actually have more than one view. You can have like a view to look backwards or some other use cases you may have. And then your pipeline will define that. It will build those views. So those views will own all the draw list data. Draw list data will contain all the information that the GPU needs to do the work for that pass. So it contains your shader bytecode, input, all the resources, inputs and outputs. So the pass's job is to query the views and then grab the draw list. So now and then store it, and then it will pass these draw lists down to the RHI, and the RHI will build a frame graph out of it. So that's sort of the high level RPI overview. Let's go into the pass system because that's sort of the heart and soul of the RPI. The pass system, so some of these slides I've taken from one of the previous presentations, the deep dive on Atom. The pass system is built with three core tenets that you can build a pass using C++, you can build a pass using JSON, and they can work seamlessly together. So you can data drive it, or you can build it yourself. And why would you pick one or the other? Here are some trade-offs. With JSON, you have quick build time. You can iterate much faster. You have ability to do prototyping. It's hot reloadable. Whereas with C++, you can have more control. There's much more complex logic. So it's a bit of a trade-off between speed and usability versus control and customization. So here's a quick example of a very simple one pass. So a pass contains a bunch of inputs. So in this case, it's a transparent pass. You have three buffers coming in, which is the depth buffer, a lighting buffer, and a light list buffer. And then your transparent pass, the cogs in the center represent the kernel, which in this case will be your compute shader or pixel shader or mesh shader. Well, O3DE doesn't currently support mesh shaders, but it shouldn't be too hard to add. And then your output is your lighting buffer. Sorry, it's kind of hidden from my. This work is so all of these resources and the shader bytecode gets sent to the GPU. GPU runs this in a multi-threaded fashion and it reads in the inputs and generates the output. And so we wanted to define that. So this is sort of you can define it using JSON, and there's slots. There's a concept of slots, inputs and outputs. So an attachment. So the inputs and outputs of the passes are called attachments. So that's the lingo that we use in the renderer. Attachments sort of form the connection. So you can have one pass that's writing to a buffer and another pass that's reading from it. So this buffer is an attachment. The attachment also means that the RHI knows how to synchronize it properly. So if pass one is writing to a resource, it will make sure that the pass one finishes before pass two starts reading from it. So we call them attachments. So here's a very simplified version of the pass tree. So you have a pre-depth pass that is writing out resources that gets sent to the light culling pass. Light culling pass will read them, write them out. Then the pre-depth pass also gets sent to the opaque pass, which can then get sent to the transparent pass. And this is, if you don't have any post-processing, the result of the transparent pass can actually go directly to the swap chain texture and get redisplayed. And that could be your render pipeline. Obviously, it's extremely simplified. It's missing a whole bunch of features, but in theory, it could work. Pass system also supports this concept of hierarchical encapsulation. So you can have a parent pass, which has a bunch of children passes. And the point is that it makes it really easy to build out your pipeline. So your passes will just pull in the parent pass, and the parent pass can then take care of all the child passes under the hood. So the higher level pass chaining doesn't have to understand how the children passes interact with each other. And the way that's set up is you have a depth buffer that comes in, that gets sent to the parent pass, and the parent pass will feed it to all its children passes. And the children passes are also linked together in some sort of chain manner. And then the output is some final output texture. So in this case, it's an SSAO texture. So how does it all connect together? This is a quick example of multiple layers of encapsulations to form a big pass tree hierarchy. So you have your pre-depth, light culling, shadows, and then if it goes all the way down to the post-processing has many, many parent passes. So you have your SSAO, you have your bloom, and then bloom is responsible. So the post-processing, the way it's chained and linked, it'll make sure when it sends this information down to the RHI will synchronize all the resources correctly, put them in the right state for the next set of work to do. And it will try to parallelize as much as possible. That's the whole point of the GPU, is to go as wide as possible. And depending on your synchronization, it'll try to go as wide as possible. So features is a quick overview when we were wanting to develop the features. The features are extremely modular and extensible. Most of the features live in the features common gem. There's a very deliberate decision because we didn't want to separate out every feature into a gem because there is some amount of friction required to enable and disable gems. So if it's all in one gem, then it's really easy to enable, disable. And these features are usually smaller in nature. They have a very small footprint, memory footprint, as well as disk footprint. So it made sense to have it all in one to make sure that anybody is able to at runtime enable and disable these features. But some features are very large, they have massive footprint, and those have been pulled out into separate gems. So global illumination is an example. It's a completely separate footprint, completely separate gem. You have the terrain, vegetation, particles is another one, but particles was done mostly because it's not an open source. It's done through popcorn effects. So yeah, so you have to sort of decide where you want to put your feature in. Does it need to go in the features gem, or does it need to own it in a separate gem? And if it's a separate gem, then a developer will need to enable the gem before he starts the project. Every feature has three core parts. There's a feature processor, there's a component, there's a feature processor, and then there's all the passes related to it. Some, depending on what the feature is trying to do, you can use existing passes. So if you already have a full-blown pipeline and you want to add a new feature, you may not need a new pass. You may just use the existing, let's say the forward pass. So you would just use the existing pass. But if you need to add a new pass, you would then add it in the JSON pass files. And then at runtime, you will add the code for the component, and then you have add all the code for the feature processor. Feature processor is a singleton. Think of it as like the manager of the feature. And the idea is that you can actually be able to get the access to the feature processor from anywhere within RPI. So it's a singleton. The components are functionalities that get added to entities in the editor. And then all the passes can be prototyped in JSON as discussed previously. So there's hot reloading, so you can actually you can make modifications to the JSON file, and it should immediately get picked up by the asset processor, and then your runtime code will update the vendor pipeline to for the changes that were just made. I've sort of used a restaurant analogy to explain the features and how it's all sort of comes together within the RPI tech stack. Components can be thought of as food items, and feature processors can be thought of as chefs that use the ingredients to create food. Food in this case is a draw packet. And then the draw packet goes to the chef, which is all the logic around sorting and culling the draw packets, because you have to filter the draw packets and send them to the right passes. So passes in this case represent plates. And then the final is everything gets sent to the RHI. Yeah. Here's how it sort of comes together. If you have a whole bunch of food items, we use the tagging system to figure out which pass it needs to go to. So you can have a tag called appetizer, and an appetizer means that this food needs to go to the appetizer plate. So, and I'll show how it works from the renderer's perspective. But the point is that the tagging system allows us to sort all the draw packets and all the draw list and send them to the right pass. And in the right, once the pass stores this information, they'll send all this information down to the RHI. So here's a quick example. So if you have your mesh data will contain all your geometry information, so like index buffers, vertex buffers, UVs, blend weights, blend indices. They will get converted into depth. So you combine it with the depth shader. Now you have a depth draw packet. The depth draw packet has the depth tag associated with it. The opaque shader will create an opaque draw packet, and it has an opaque tag from it. Now you may wonder who's telling us where these shaders are coming from. Well, that is the job of the material system. So the materials define, and we'll go over that in the next few slides. So they have a opaque tag. The sorting and culling code here will essentially actually do all the custom culling, occlusion culling. So you don't want to send packets to a pass when they're not even visible. So it will do that, and based on the tag, it will send it to the shadow pass, and for the opaque tag, it will send it to the opaque pass, and that's how it does its sorting and culling. So here's a quick example of how Panda is rendered. You have your mesh. Mesh is an asset. It has a bunch of materials. Materials is also an asset. We'll go over the material system in a bit. Material tells us, hey, this mesh needs two shaders based on the material pipeline. So this is a forward pipeline. It needs a depth shader and a material shader because it has a depth pass and a forward pass. We'll create draw items out of it. Draw items combines all of them together to create a draw packet. The draw packet the correct one gets into the shadow pass and the opaque pass, which then gets into the RHI, which is then creates the GPU commands out of it, which the GPU executes on to render the Panda. So the focus of the render is that it is easily customizable. You can copy the main render pipeline and build your own if needed. You can add shaders, materials, and passes with zero C++ interaction. So if somebody's already built the skeleton of a feature, you like all the parts within the C++ side, you really should only be focusing on iterating on the shaders and the materials and passes, because that's what controls how a feature will function. And all those components of feature process are self-contained. So there's very little spaghettification happening. So there's no colossal word. So I've worked on many engines across many games, and pretty much all of these engines, the biggest problem was that the render pipeline was always hard-coded in C++. So you have to be a really advanced like graphics engineer to sort of go into this code, understand if you have to understand the whole rendering pipeline, because you can't just go in and start modifying C++ code for just one pass, because you could have deep integrations with other passes, and it may support. So it's all like spaghetti files. So like if this pipeline then do this, if this pipeline, then this pass connects it. Like it's all in C++. So it becomes really hard to understand. So all of that is gone now. We did have plans to convert the render pipeline, which is all in JSON, into a GUI. So just like a material canvas, so you can actually see how all the passes are connected easily. It's just like an offline tool. If anybody has time, they can implement this, but currently it doesn't exist. But it would be easy to add because it's just a GUI over JSON. And then we try to make sure that you can easily add custom BRDFs. So for PBR shading, you can, even the shader code, we try to keep it as independent, as decoupled as possible so that you can modify one area without actually having to understand and touch other areas. So here's a quick recap of all the features that we currently have. I'll try to capture the important ones at the least. So we have 4+ rendering, which uses clustering. It's a hybrid light culling solution. So that's the core of the main render pipeline. You have a fully PBR shading model. So it has support for specular anti-aliasing, multi-scattering, compensation, subsurface scattering, and anisotropic BRDFs. There's support for area lights. So you have sphere, disk, rectangle, capsule, linear, transform, cosine. We have terrain and vegetation support. We have shadow atlasing. So you can have soft shadows using ESM and PCF. You have global illumination, which is done. We used NVIDIA's RTX GI to help support global illumination. But there are some issues around licensing with the shaders for this solution. AMD actually released their own open source solution, so that would make a really good candidate for O3DE as an alternative. And this is where the gem systems would really benefit, where you can just throw in another gem with the AMD solution and people can pull in whichever one they need. There's the post effects layer technology. So you have the concept of volumes, areas, and weights, and then you can attach like all the various post processes. So like bloom, depth of field, SSAO, eye adaptation. We also have full on ASIS pipeline, which is what is used in movies for the most part. But now pretty much games have adapted it because they are pretty efficient. We have hybrid screen space reflections. So it essentially does screen space rays as well as it switches to ray tracing API. So they're very good. We have a full-on anti-aliasing, multiple anti-aliasing solutions. So we have temporal anti-aliasing, multi-sample anti-aliasing, and subpixel morphological anti-aliasing. I think we don't actually use SMA a lot, but it's there depending on what if you are using a default pipeline, SMA makes sense. And then we have stereoscopic rendering support. So this is just a subset of features that we currently support. Of course, you can provide alternatives. Some of them have their own gems. Some of them are in the featured common gem, but it's easy to update and fix stuff. If you press the tilde in the editor, it will bring up your MGUI menu. And that has all the tooling that's built in for the renderer. So you have your GPU profiler. The GPU profiler will show all the passes that are running and how much time it took. This functionality, the timestamp functionality only works on forward GPUs. So it'll work on your PCs, your Linux, and actually won't work on the M1 Max because M1 Max use tiled hardware now. But there are native tooling that you can use to get time. So Apple has really nice tools to do GPU captures, and they'll provide tooling. It just won't be runtime, so you won't be able to see it at runtime, but you can do a capture and then see it. We have a pass tree tooling, so you can actually see all the passes, see the outputs of all the passes that can help you debug the passes across your pipeline. You have your CPU profiler. The CPU profiler essentially shows all the we have a whole bunch of what they call markers all throughout the RPI and RHI code, and you can always, we've disabled some because you don't want it to be too noisy, but any type of engineer can easily go and enable them or add more if needed. Speed profiler is there. It tracks multiple threads, so you can go down, you can see what the main thread is doing, we can see all the other threads are doing, and if there are gaps, you should be able to see, hey, is it waiting from another thread, or maybe it's missing a marker, you can add a marker, but the profiler is there. And then there's a GPU memory profiler. GPU memory profiler tracks all the GPU memory. So not only transient memory, but also persistent memory. And it tells you if it's a buffer or an image. And it's a really good way to track GPU memory usage. CPU memory is tracked in a different tooling, so it's outside of the O3DE renderer. CPU memory would be tracked as the O3DE, as the whole engine uses CPU memory. So that is tracked outside of the atom. Materials. Let's go over materials. So we have a full-on material editor application. So it lets you build materials. You can use custom materials, the materials that come with the engine, or you can create new ones. And how does the system work? So we already support all the shaders to do with PBR shading. So the PBR shading model, the way it works is you have your properties like your albedo base color, metallic, roughness, specular reflectivity, and then your shaders uses all the PBR shading models. So you have your microfacet theory, so it uses your GGX, your BRDF will contain all the calculations related to how to capture specular and diffuse. So you can build materials such as wood, metal, concrete, and other materials. And we also provide material types that support more complex materials. So clear coating, subsurface gathering, and etc. So here's how it works. So materials, there's this concept called dot material type. Dot material type, essentially, the engine already comes with base PBR, standard PBR, enhanced PBR, and also standard multi-layer PBR, so you can have multiple layers. But each one of these files contains the layout of your material. So it will have all the floats, all the properties that we just discussed. So it'll say, hey, you need to, this is the layout of this material type. And then from the material type, you can essentially build the material. So material types already exist. So a bunch of them already exist, but you can create a custom material type if you need. Then you would build a material dot material asset out of it. So let's say a brick dot material can reference the standard PBR, and then it will provide the values for those floats and integers or booleans, whatever the data that's in the layout for the standard PBR. So the brick will say, hey, my albedo color is this, which is the texture. My metallicity value is this. My roughness value is this. And then you can have inheritance. So you can have red brick is inherited from the brick. So the red brick would only change the albedo color, and it will inherit all the properties for roughness and metallic and specular reflectivity from the brick. And then you can build your custom material that can point to a custom material type. So that's how the hierarchy is set up for the material system. At runtime, you can use it creates the dot material file, and it'll create a material runtime object. So that's the actual object that's created at runtime. You can have many material components point to the same material that you did. So you can have, let's say you have three entities, they all have a different material component, but if they use the same material, they'll point to the same material. But you can also force a material to be unique. So a material can point to a material component can point to a material object, which is unique in that there are some values differ. So that's how it's sort of material system is set up at a very, very high level. We also have material canvas. So material canvas is lets a developer build new materials and actually create the kernel, the shader on how it needs to be, how it will be shaded using the script canvas tool. So you can pull in the right nodes, link them all together, all the functionalities there. I mean, obviously this is a much more complex topic. I'm just providing you a quick overview that it's there. It uses auto code generation. It has template files for the shaders that it needs to pull in, and it will auto generate the final shader for you, and that gets pulled in. That can be pulled in for your custom material type. O3DE has this really cool concept where materials, lighting, and the material pipeline, they're all decoupled. So we just went over the material type files. So material type defines the layout, and then you can build material instances from the material type. So your material graph is the auto-generated code that can come from material canvas, but it doesn't have to be from material canvas. You can just build the material type yourself. Then you have it has a concept of lighting model. So lighting model can be base, standard PBR, enhanced. So lighting model essentially defines how to pull in lighting specific shaders. So we have shaders that just contains lighting information. So we'll pull them in based on the material type. And then you have this concept of material shader code. So base PBR has called out AZSLI, and then this material shader code is what defines the material pipeline. So the idea is that you can create more than one pipeline very easily. Before, when our first implementation passed, we only had one pipeline. So this main material pipeline was embedded in the material type, which made it really hard when you wanted to add other material pipelines. So we decoupled everything, and it's just we did it through indirection. So material shader code pulls in, defines all the passes and all the shaders related to those passes. So if it's a main material pipeline, you have your depth pass, shadow pass, forward plus pass, and a transparent pass. If you have a deferred pipeline, then you have your depth, shadow, and a deferred pass and a lighting pass. So that's where the difference is, and a transparent pass. And then all of this essentially gets fed to your render pipeline. And so this is how we've decoupled materials from lighting from pipeline. So if you want to just introduce a new lighting model, you should in theory just have to add a new lighting model and then make sure that it gets supported easily across all the pipelines. If you just want to add a new material pipeline, you should just in theory have to create just update the boost PBR.AZSLI, add the information, the new scripts, the new shaders, and you have a new material pipeline. So this is really cool if you are evaluating this render for your game and you have a very specific game use case. You can easily update the renderer for your use case. Okay, that's all of the RPI. All of the systems within the RPI that I think we should touch on. There's a lot more going on in there that is not out of the capacity of this presentation. So RHI, you have your RPI that feeds all the information down to the RHI. RHI is composed of the common layer, DX12, Vulkan, and Metal. These are different gems. So RHI only has all the common code for how to create the frame graph, and then DX12, Vulkan, and Metal has all the driver specific API. So how the RHI works at a very, very high level, it essentially has three phases. You have phase one, where you build your frame graph. So from all the past tree, we essentially flatten out all of that work into one acyclic topologically sorted graph called frame graph. So you can have multiple passes. So like that's how VR works. VR will have two separate pass trees, one for the left eye, one for the right eye, with its own inputs and outputs. It all gets flattened. So it all gets into the RHI. RHI will flatten it all out into one big frame graph. And all RHI cares about is give me the GPU workload, which is the shader information, inputs and outputs. And that's it. That's all I care about. I don't need to know anything about what type of a pass it is. Is it a parent pass or a child pass? It doesn't care about any of that. All of that complexity lives in the RPI. When it comes to the RHI, it's literally turns into scope. Scope one is just one unit of GPU work. Scope two is another unit of GPU work. So in this case, scope one writes to a render target and scope two reads from it. And there you go, there's a connection there. So now RHI knows I need to synchronize scope one with scope two. So make sure scope one finishes writing to the render target and then add the correct barriers and fences to start to scope two. So that's how RHI works. It simplifies the whole pass tree into one frame graph. Then there's phase two. So that's phase one. Phase two is it will then go through all the scopes and compile all the resources associated with it, with one caveat, and that caveat is shader resource groups. These are very specific objects that are used to bind. So that's the binding that contains all the binding information. So if you have your shader, it needs all the inputs and outputs. Shader resource groups is how you bind those resources on the GPU. So this is done in parallel because you can have many millions of resources in theory, and you don't want to single thread that. And then you have your actual execution. So this is where you build your command list. And the way it does it, it figures out, it will create multiple groups. All of these groups are run in parallel. And within the group, it creates execute context, which are also run in parallel. So it's extremely parallelized. It has criteria on how wide to go and how vertical to go. And it will try to pick the best configuration based on performance. So it will merge classes. So one group can handle 10 scopes, or one group can just one scope can have, let's say, thousands and thousands of meshes. So then it'll go wide internally. So it all depends on how the framework is set up. So this is a sort of high level overview. There's a lot going on. And there's a presentation done, the deep dive on RHI. That's a good presentation to look at for more details. RHI supports asynchronous virtual texture streaming. So we provide asynchronous streaming by loading in the base MIPS first, and then we'll load in new MIPS as depending on how the character moves and the camera moves closer to specific meshes. And these MIPS are loaded in asynchronously. So there's a copy queue that's set up separately, and it's loading in stuff asynchronously. We also have virtualization support. And we actually did it using drivers. So drivers have this cool concept called tiled resources. So if you have your virtual texture UV space, it's split into tiles. And then these tiles have a page table, which knows exactly. So F tile points to 7 memory, and in the physical memory, it will point to 7 memory. So we actually tell the driver, hey, can you make B, E, and G resident? And then the hardware will take care of the rest. It will go in, so it knows B, E, and G points to uh, this physical memory. It will make sure that they become resident, and then that's how they get pulled in as needed. So we have virtual texture support, but not built in within the engine. We use a drivers for that. So it's only supported on DX12 and Vulkan, not on Metal. Although adding it for Metal would be not a hard task because all the APIs already exist and it's supported. We also have support for transient memory aliasing. So if you want to conserve GPU memory, if your scope 1 renders something to run a target A, scope 2 reads from it, but then your A is now free to be used. So then scope 3 can reuse the same memory because scope 1 is done with it. So instead of creating A, B, and C, you just go A, B, and A, and that's how you serve. This is a very generalized, oversimplified example, but that's sort of the RHS. The RHI has a complex shader pipeline, which I'm sort of just going to skim over. We have a shading language called OZSL. This under the hood is HLSL with some metadata. We have our own compiler, AZSLC, and that spits out HLSL during asset processing time. HLSL goes through DXC, which is another compiler by Microsoft, which spits out Pixel for DirectX 12, SPIR-V for Vulkan, and for Metal, it spits out SPIR-V, which goes through another cross compiler to spit out MetalSL. Apple have released tools to go from Dixel to MetalSL, but I have an RFC up for that, but we don't have integration for that tool. But that would be the right way. The only problem is that the min spec will be iPhone 11 and not iPhone 10 or iPhone 8 right now. And then all of this gets into the runtime for usage and the layout information related to shared resource groups. RHI has a lot of topics that I'm not going to go into. You can refer to this slide. It talks about how to efficiently resource bind, basically explains what SRGs are. It explains how the resources are tracked, so barriers, fences, semaphores, and how we encode in parallel. So there's 2 slides, 2 presentations. Definitely refer to them if you are curious on how RHI works. It's a very complex piece of technology here, and if you are curious, take a look. RHI also provides support for ray tracing. It provides support for indirect draw. So indirect is supported in RHI. It just Nobody has built a pipeline out of it. Or people have, but they haven't contributed back to the engine. It supports subpass. Subpasses allow you to merge passes. It's a GPU optimization. It also supports pipeline library. There's a whole complex set of code that's set up to compile your PSOs at runtime. So if you have a bunch of shaders, bytecode that comes in, you actually have to convert it into a PSO. PSO is the object that gets fed to the GPU, and it contains all the information like the shader bytecode, the pipeline information, the render state information, all the inputs and outputs references. So you need to build that, provide the layout information, and then so all of that happens multi-threadedly. And we also have a lot of logic where when a shader is destroyed, it actually writes out the PSO to the disk, so that the next time you ever want to run it, it will load it from the disk instead of building it from scratch. And then we have native MSAA support, and we also have variable rate shading support, although it's not being used, I think, in any of the automated assembly, but it's there to be used if you need. Okay, this is the last slide. I'm sorry, we're kind of going overboard here, over the time limit here. So you have I've tried to encapsulate all of the communication in sort of one slide. It's hard. I've taken some liberties with some of this setup. So you have your on-system tick, which gets called a reclaim, which is split into simulation tick and render tick. Simulation tick will go to each feature processor called simulate on it to do simulation work. Then there is, so this means that it's going wide. So all the simulate goes wide. Then there's a sync point. The sync point is prepared when you start. Then it'll go wide again to do all the call render. Render will create all the draw packets for all the passes. And you would have already created the passes from before when it loaded the render pipeline. Then there's another sync that happens on prepare render, and then it goes into the RHI land. RHI will try to create the frame graph, and essentially each pass has 3 callbacks, and it'll call these callbacks. So RHI will go through each one of these passes, and it will call these callbacks, and these callbacks essentially tells the RHI, here's my shader, here's my inputs, and here's my outputs. And then RHI will build a frame graph out of it. Then it will do the exact same thing for compile resources, except for SRGs. SRGs, the information gets queued, and then RHI will go wide for the SRG compilation. And then finally, it will create groups. This is all happening in one frame. So it'll create groups, it'll call execute, it will call into the build command list function. It will build the command list for each pass and then call execute. So that's sort of the very, very high oversimplified version of how the renderer works. So what's next? There's a lot of stuff that I haven't had in touch. Obviously, you just can't. But if you have questions, we can obviously reach out on Discord. The RHI, the O3DE render code is we try to be extremely modern. It is very well documented. We've had strict coding guidelines. It's C++, I think 23 now. I forget now. So it's not like really bad because I worked on engines where they have really bad coding guidelines, just bad code, spaghetti code everywhere. And we've tried to keep ourselves and set ourselves to high standards. So if you have any questions, don't feel afraid to just jump into the code, look at the header files. They'll hopefully provide a lot of documentation and guidance on how the code is set up if there is no outwardly documentations related to it. So what's next? So next is there's a team, external team working on multi-GPU support. This is an insane amount of effort, which will convert the whole O3DE engine and allow it to essentially send workloads across multiple GPUs. So think of it as like if you have a game and you want to do split frame rendering, you can do one side to one GPU, another side to another GPU, and a third GPU can composite it. Or you can do physics on one side and rendering on one side. Or you can do like training, which is how a lot of the LLMs are getting trained. You essentially send workloads across multiple nodes. Although O3DE can't support LLM training at the moment, but you can. And if you do add support for that, you can do it multi-GPU wise. There's a huge effort that's going on for function constants. It's a replacement for shader variants. I didn't really touch shader variants, but that's a whole another topic in itself. But in theory, you don't have to build, you can actually build a perfect shader variant at runtime. So for non-console platforms, which is very attractive if it's supported. But for consoles, you can't do this because consoles doesn't let you build PSOs. It doesn't let you build do this on at runtime. You have your render pipeline support. This is also another team is working on providing subpass support. So it currently exists on the RHI, but this will make it available across the pipeline, the render pipeline. So you can actually build pipelines with subpass support. This is a big deal because this is a huge optimization for mobile and VR. And there's a bunch of fixes that are happening on mobile and VR. There's one slide I have especially for, given the enormity of this feature, I devoted a separate slide for this. Virtual geometry solution. This is essentially a nanite type solution. Obviously, it's not merged in. It's still, it was built by an external party. And the thing that I wanted to point out was it kind of goes to show the power of O3DE, the gem system, the modularity, the extensibility. They probably evaluated multiple engines and they're like, hey, this is the best engine to do this work and prototype this feature. And they were able to build it. They built it without even ever, we had no idea. It literally just popped up at GDC. So obviously they were able to figure out all the problems and kinks and build a nanite type solution. So in this case, you have 4 billion triangles easily running at 60 frames a second. And all these clusters are just popping in and popping out, and you have no idea under the hood, which is exactly what nanite does. So a solution like this is buildable, is easy to build, and that goes to the power of the modularity of this engine. We would want to reach out to them and reach out and
I
hope.
am actually, so while you've been giving your presentation, I've actually been emailing with back and forth with them.
Awesome. Okay. It'd be awesome if they can provide that. This will essentially put us on track, similar track of like to our the peers of O3DE. That's sort of the end of the presentation. I provided some roadmap. Okay, yeah. So there's the Discord link. There's the roadmap link. So please take a look at the roadmap to see what graphic features. I've sort of mentioned some of the graphics features that are coming down the line, but take a look at the roadmap. If you have any questions, there's the link to the repo. There's a SIG-Graphics channel. So reach out to the graphics channel, and hopefully there are folks there that can help you if you have any questions. And at the end, I want to say thank you. What I have shown is an effort by a lot of folks who are still currently with the team. Some of them have moved on, but a lot of them are still here. And you know, very grateful to all the work that everybody has done to sort of make this thing a reality. I mean, I still remember 4 years ago, this was, or 5 years ago, possibly, that this was sort of like a dream. Like, hey, can we build something that is AAA, is modular, is anybody can work on it, and easily customizable, so you can have a long shelf life. And I think we've made that happen. Although I would like to see more games and more use cases. And that's it. Anybody?